Hey, welcome back. This is now 7.5. And it's basically an application of integrals to physics problems, in particular determining work. So just some minor points. 1 mile is equal to 5,280 feet. And then 1 ton is equal to 2,000 pounds. And then the units for force we'll be using will be either newtons or pounds. And okay, so we'll begin with just defining what the heck is work in case you're a non-physics person. And work you can think of as a force applied over some distance. So maybe like pushing so one of the applications we'll look at is launching a rocket. So the force involved, the work involved in moving a rocket from the surface of the Earth to cloud level. Right, so you have to apply some sort of force over that distance. It'll be, in that case, a variable force because the higher you go, there's less gravitational pull. And then there's times the distance traveled. Okay, and it's a very simple formula. You'll see it in the beginning exercises. Let's maybe look at kind of the exercises here where you're just applying it 3 years later. So for example, problem 5, we want to hit the button again. There we go. Problem 5, we want to figure out the work done by a constant force of 12. So it says you're moving a 1,200 pound steel beam 40 feet, so that you're going to have to apply a force of 1,200 pounds to move it. So the force is going to be this 1,200 pounds, and then where the distance traveled is going to be this 40 feet. And so the work is just going to be 40 times 1,200, which I believe will be 48,000 foot-pounds, presuming I know how to multiply in my head. Okay, so let's make sure, yeah, 48,000 foot-pounds. You just take the 2 units and put a little dash in between them. The trouble with these kind of problems sometimes is making sure make sure all the units align to whatever answer you need. So you see in problem 1, they're giving you information in terms of tons and miles, but their answer needs to be in foot-pounds. Okay, so you need to make your conversions in an appropriate fashion in order to pull off the work answer. Okay, so anyways, ultimately we won't have just a constant force. Those problems are a bit silly, a bit too easy. Those are high school problems. We want to consider variable force problems. And we'll use integration in order to figure out the work done. Okay, so for example, the launching of the satellite again, in the beginning, you have to use a lot more force than you would have to use if you're way out there in outer space due to the gravitational pull, right? So there's a variable force, and you'll have to kind of figure out what that force formula is, and then you'll just use the integral to add up all these little work packets rather over some sort of interval. Okay, so going from A to B, here's our force formula, and then the Riemann person this time is going to be collecting a bag of work elements. Okay, so this work element is going to be based off the rectangles, and you kind of just think of the rectangle's area as now representing work, right? So this rectangle located at position x of I has base change in x. The work element now, instead of before what we saw was maybe an area or a volume formula, now we have a work formula. That's just going to be f of x sub I, the amount of force required to move it in that interval to produce a movement, times the distance traveled. Okay, so times the distance in that little increment is just change in x. And then your Riemann person runs across and collects all those elements. And then we take the limit of it and we get our integral, which will just be big F of x dx from A to B. Okay, so pretty simple. Anyways, let's go ahead maybe and take a look at some of these types of problems. So the first variable force problem you see in the homework is the Hooke law problems where you're stretching or compressing a string, rather a spring. The formula for Hooke's law is going to be big F equals K times D. So basically the force required to stretch or compress a spring is proportional to the distance of the displacement. Okay, so the more you smush it, the harder it becomes to smush, and likewise, the farther you stretch it, it's proportional to that distance of displacement. Okay, so the way they've kind of done the diagrams in the book is not the way I choose to do it, but I just want to be consistent with what the book is doing. So please forgive me if this is not all that intuitive, but it's just a matter of me trying to be consistent with whatever the people in the book are doing. Okay, so let's look at, I guess, problem 2. And they're working with a spring of 15 inches. That's what it says in the problem. Okay, so here's my spring. And the way the book is going to set up this particular problem is put the 0 on the number line there, and then put 15 when the spring is in its rest position right there. Then to indicate a stretch, what they do is kind of tack on another distance. All right, so this to here is a stretch no, they want to compress it. I'm sorry, that I'm thinking stretch. So to compress it, what they're going to do, I think in the book they just draw a whole nother diagram, right? And then they kind of like, hey, it's been smushed to right here. So this is from 0. No, that's, again, I'm doing it wrong. They're going to compress it in this direction, sorry. So they'll compress it out to here, and then here's your spring again. Okay, sorry. So they've gone out to 5, and it looks like that in the book. Okay. They say in the story problem that it takes 7 pounds of force to do that. So again, you're working with this formula, the Hooke's law formula. So F of 5 is going to be equal to 7 pounds of force. And you could use that information then to solve for the constant in Hooke's law, that K value. Okay, so F of 5 is 7, so we're going to write 7 for F, and that'll equal K times this displaced value, which is 5 in our problem. So K, if you solve, will be 7/5. And then we have our formula. So we'll write F of X is equal to 7/5 X. And the end problem, they want to know how much does it take, how much work is done in compressing at 8 inches. So in the integral, we'll have the formula for force, and then we want to compress it from 0 to 8. Okay, and the integrals are fairly easy to kind of manipulate with regards to compression or stretching. So if you're going to stretch it another 8 inches, usually you could just go from 15 to 23. I'll show you an example of that. I'll probably do all of these. But anyways, here we have 7/5, then integrating x squared over 2 from 0 to 8. So I have 7/5. X squared is 64 divided by 2 is 32. And then minus 0, that will equal 224 over 5 inch-pounds. Okay, for the amount of work. Okay, so that's the weird thing is the orientation. You'll find for these string and problems that they always have every author has to rewrite it in their own orientation. I was thinking they have a team of physicists currently working at envisioning new ways of orienting the springs. They'll orient them vertically, horizontally, and then put the, x equals 0 here, x equals 0 at the end, flip it, put it backwards. It's just a nightmare, but like I said, I'm just going to go with whatever the heck the book does. Anyways, let's look at number 3. So number 3 is kind of the other orientation where you're stretching instead of compressing. The book doesn't really indicate how they want you to orient it, but I kind of tried to keep it consistent with what they've done here. So anyways, you're going to have this picture now. They don't really tell you the length of the string or the spring, but I'm going to put the 0 position here this time. And then what they're going to do is stretch the thing another 30 centimeters. So I'm going to say, okay, if I stretch it, it's going to pull it out to position 30. Okay. All right, so reading the problem, use Hooke's law to determine the amount of work. A force of 250 newtons stretches a spring 30 centimeters rather. How much do I have to do to stretch it from 50 to 80? Okay, so then ultimately I'm worried about stretching the thing from 50 out here to 80. Okay, I need to, again, get my hands on that constant value. So my force function from Hooke's law, F equals K times D. In this case, they're saying the force is 250, and that displaces the string 30 centimeters. Okay, so I can solve for K, that'll be 25 thirds. So my force formula is 25 thirds X. And then in my integral, I'm going to go from 50 to 80, and that should do the trick. Okay. If you have to work in physics, hopefully they're a little bit more rigorous as to how they're defining the system. These string problems come up again later in differential equations too. That's a huge part of differential equations, because you could model so many phenomena in terms of kind of springs moving back and forth, but it'll be more apparent there. And I'm not going to put these questions on the test. I'm not putting work on the test, so you need not worry about becoming a master at it. Anyways, integrating here, you get 25 x squared over 2 times the 1/3. It gives you 25 6x squared, and I need to go from 50 to 80. So this will be 25 6 times, I went ahead in my calculator earlier and figured this out, 97,500, and then evaluating that, I'll give you 16,250 Newton centimeters. Okay, great. The next one, then the last Hooke's law problem in this section is a little different. What they kind of do is work with the integral first, and then you use that to determine your K value. So anyways, the work involved is 6 joules, and that will stretch the spring from its natural length to 0.5 meters away. So in this case, I'm gonna label the right-hand side as 0, and then I want to stretch it an additional distance of 0.5 meters from its original resting place. So with regards to the formula, I don't really know it at this point, right? So I know it's going to be F equals K times some X, where K is an unknown. And I want to, at this point, I have not the force, but the joules, so the work amount. So looking at the formula for the integral to find the work, it would have been some constant K times X, let's factor out the K, and then if I displaced it from 0 to 0.5, I'm going to end up with 6 joules. So you have to use the integral now here to solve out for the K value, and then you can answer the follow-up question they pose. Okay. All right, so anyways, in this problem, then you'll get K x squared over 2, evaluated from 0 to 0.5 equals 6. So it'd be K times, in this case, it'll be 1/4 equals 6. I lost my 2 somewhere, so it would be 1/8 at the end of the day. And then you have to plug that in, right? So this is really, what is this? 0.5 squared is 1/2 squared. 1/2 squared is 1/4, and then there's that 2 in the denominator, so that would be 1/8, and then minus 0. Okay, so if that's clear. And then multiply both sides by 8, so the k value is 48, so our integral is really 48x dx. And then to the follow-up question, they want to know how much work is required to stretch the spring an additional 0.2 meters. So in this case, you're stretching an additional 0.2 meters all the way up to 0.7, so you're going to go from 0.5 to 0.7, and then you're going to evaluate that integral, okay, for your final answer. Okay. Okay, so we'll leave that one to you, and let's move on now to what next? The launch problem. Okay. So this problem here, we're thinking about launching a spaceship off the surface of the planet, and we are using, so they give you all the formulas in the book here that you would need, and I can't find it. Oh, there it is, Newton's law of universal gravitation. So we'll just consider the g, so it equals f equals g times m1 m2 all over d squared. We'll just combine the gravitational constant and then the m1 m2 into one huge constant. So for the gravitational problem, which is basically the satellite problem, our formula will be f equals k all over x squared. Okay. And it works a lot like before. You just kind of have to figure out this constant, and then you're integrating from one position to some other position. There's our pictures for the spring there on the right. Now we want to think about launching a satellite off the planet. Okay. Okay, so let's take a look at these kind of problems. Here we have problem, what is this, 5. Neglecting air resistance, the weight of propellant, yada, yada, yada. Determine the amount of work to propel a 7-ton satellite to the following heights. Okay, so first 100 miles above the Earth, and then secondly 800 miles above the Earth. The 4,000, you got to be aware that when the satellite is on the face of the planet, it's not exactly, at height 0. You're going to presume when the satellite is on the planet, it's already kind of positioned 4,000 miles above position 0. Okay, so there's this radius of the Earth, which we presume is 4,000 miles, and then the satellite, which I'll kind of visualize with the kind of looks like a TIE fighter from Star Wars, is sitting on the planet, okay? And then use the weight of the satellite as kind of the initial force. So it's a 7-ton satellite. Our formula, F equals K all over X squared. So to get the K value, replace F with 7, the weight of the satellite, and then we have K all over. So the weight of the satellite is 7 tons, right? So that means that's when it's 4,000 miles away from the center of the Earth. Okay. I'm not going to multiply this thing out because it's such a big number, so I'll just write K is equal to 7 times 4,000 squared. Okay. And that gives us our formula for force that we're going to use in to figure out the work, right? So that's our force function is 7 times 4,000 squared all over k squared. Let's rewrite that as x to the negative 2, all over x squared. Let's rewrite it as x to the negative 2 for integration purposes. So our first case, we want to figure out how much work is done in moving 100 miles above the Earth. Again, you got to be a little careful because we're already kind of positioned at location 4,000 miles beyond from the center of the Earth, right? So I'm actually moving from 4,000 to 4,100. Okay, so again, our formula for force this time, 7 times 4,000 squared, and then x to the negative 2 dx. Factor out your constants. Integrate the x to the negative 2. That's going to be negative 1 over x, x to the negative 1 over negative 1. And then integrate from 4,000 to 4,100. Okay. Right, and then it's just computation. So 7 times 4,000. And then you have minus 1 over 4,100 minus negative 1 all over 4,000. And then go to your computer of choice and evaluate that thing. So I got 28,000 over 41. Part B is almost the same thing. This is part A. The only difference with part B is you're traveling from 4,000 to 4,800. Okay. Problem 6 is a little bit different because now you're on the moon, so there's some unit issues. Maybe you have to recompute the gravity, the K value for this new setting. But the weight this time, which you can think of it as the force, is going to be 12 metric tons on Earth. But the problem is we're not on the Earth, we're going to be on the moon, right? So the picture this time maybe a smaller globule here. The satellite now, or the lunar module, I guess, is on the moon. And what does it say? The radius of the moon is 1,100 miles. Seems like the moon is pretty big then. So that radius is 1,100. And the force of gravity on the moon is 1/6 that of Earth. So the force, let's call this Fe, and then Fm for moon is 1/6 that of the Earth. So whenever you say that word of, it usually just means to multiply. So we'll just multiply. 12 over 6 is 2. So that will be our force value in our formula. So the F equals K all over D squared. The D value here is 1,100 now. And so our K value is going to be 2 times 1,100 squared. So our integral, you got 2 times 1,100, 1,100 squared times x to the negative 2 dx. And we want to know what? We want to move the lunar module 90 miles above the Earth. So 90 miles above the moon. So I'm starting at 1,100, and then I got to go to 1,190. Okay, and you could compute that on your own. I just wanted to kind of set it up for you. Okay. The next type of problems we have these. So these get a little bit more complicated, unfortunately, for us. And usually I don't really have a good title for them. But what we're doing is pumping either some sort of liquid or fluid out of a container. The other types of problem are these chain problems. So let's just call them fluid and chain problems. And we want to figure out the work done and moving a bunch of liquid out of maybe a fuel truck or a cylinder of some sort. And okay, so the deal will be is you got to slice. What you're going to do is slice the fluid up into a bunch of geometric objects, and then sum up the work required to move each individual geometric object out of whatever cylinder it is or thingamajig it is you're working with. So in problem number 7, we have a cylindrical tank, and we just usually consider the cross section of it. So drawing out the cross section of the thing you see on the right there, it's a box, right? It's going from the actual dimensions of the cylindrical tank. The radius is 2, and then the height is 6. 1, 2, 3, 4, 5, 6. Okay, and our Riemann person is going to be adding up the work required in order to pump all of these disks of fluid out of this cylindrical tank. So how far do we have to move these little disks? I have to move each disk to ground level. So right now the spiel is this cylinder is below the ground. Here's the ground. And I need to move all of these disks of water out of the tank. So I need to move it out of the tank and then above the ground. Okay. So for this particular disk of water sitting right there, and you have to imagine it in 3 dimensions, this particular disk located at position y sub I need to move it from this position out above the ground. Okay. And again, what you're kind of doing is thinking, all right, that purple rectangle is the cross section of this disk. Okay. And the Riemann man is going to go through and kind of figure out how much work is involved in moving each one of those disks of water out above ground level. Okay. So first off, there's kind of a force involved. How much force is required to move that disk? What is kind of the weight of that disk? And there's 2 parts to that. There's the what's called the weight. Well, the weight of just a cubic meter of that fluid, and this fluid here is the water. So the weight of this is 9,800 newtons per cubic meter. And then on top of that, you want to know kind of the volume. So it's always going to be kind of a weight density times the amount of the particular fluid you're dealing with. Okay, so here we have 9,800, and then we want to multiply it by the volume of that disk. So it'll be 9,800, and then to get the volume, it's going to be a formula for the volume of that particular disk, which in our case is pi r squared h. So the height value is going to be change in y, and then the radius value is going to be given from the formula for what is the radius of, so it's the distance from here to here, right? So it's the distance from the axis to the side of the container. And that's constant throughout the whole cylinder. So in that case, the radius is just going to be 2. Okay, so the volume of that one little disk that you're moving is going to be pi r squared h. So pi, the radius is 2, so it'll be 4, and then times the height, which is change in y. Okay, so that's kind of the weight of that particular disk, and then we need to multiply it for work times the distance that particular disk has to travel. And each disk is going to be traveling a different distance, right? So that disk at position y sub I is going to travel a lot farther than a disk positioned at y sub j, right? So we need a formula to determine how far each individual disk is going to be traveling. And so to figure that out, well, it's just going to be this height, which is 7, minus the position of the particular disk, which in this case is y. So for y sub I, the distance traveled there has to be 7 minus y sub I. And you see that kind of given in the picture on the right. Okay. Okay, so the integral we're working with then is going to be, the Riemann person is running across gathering all these work packets. So the work overall is going to be the integral from 0 to 7 the sum of the work required for each disk going from position 0 to position, well, and 7 is the top, right? That's ground level. So we don't actually have water all in that entire region. The cylinder is buried below the ground for some weird reason. It only goes up to 6, okay? And then we're adding up the work packet. So, whoops. So this should be force, the force increment times the distance that each has to travel. Okay, so the work increment is 9,800, and then we have pi, and we want to put the delta y at the end, times 4, and then we have the 7 minus y, and then dy. Right? We can factor out any constants, of course, but I hope that you can integrate that guy, and you should end up with 9,40800 pi if you went ahead and did that on your own. Okay, what problem was that? That's problem 7. I just want to make sure I got it. So I don't have any mistakes in there. Yeah, I think that'll be good. Okay, let's look at number 8, which is a little bit different because now the objects aren't going to be sort of non-variables. So the radius in this first problem, number 7, the radius was constant. The radius was always 2 of each cylinder. In problem 8, the radiuses are different, right? So problem 8, we have a conical tank, and it's the same problem. We want to pump all of the water in that tank out above the top edge. So first off, I'm going to re-envision it as the cross section of the tank, like this. The tank is 8 feet across the top, so this will go over 1, 2, 3, 4, and it's 6 feet high. 1, 2, 3, 4, 5, 6, and okay, so we're thinking of each one of these things as a disk of some sort of fluid. Do they tell us? Yeah, it's water again. So we need to know kind of the weight of that particular disk of water. So we'll call that F, the force increment. And so to figure that out, we need a weight density times the volume. Okay? So basically the weight of the water per unit area times the amount of area is how you think of that. So the weight density is given in the problem at 62.4. And then you want to multiply that by the volume of that particular disk. So again, that's pi r squared h, but the problem now is the radius is not going to be a constant. Okay. This orientation, Riemann person is running up the flagpole, and we need to get our hands on the radius. Okay, so I need a formula basically for that straight line from 0 to whatever. Okay. And if I figure that out, then at any position y sub I, that formula will give me the radius. Okay. So to get that formula, you can use slope. Y equals mx plus b, right? So the slope is up 6 over 4 times x plus the y-intercept, which is at 0. Rewriting that a little bit, y equals 3/2 x. Then for our orientation, we want it in terms of y, so I'll multiply both sides by 2/3. And that gives me the formula for the radius. So that's what's going in here in our force increment formula. Okay, then we need our work increments, which will just be the distance traveled times the force increment. So the distance traveled this time for any position located y sub I, it's going to be the complete distance from the bottom to the top, which is 6 minus the location of the particular disk. So if that is y sub I, like it is in this case, the distance traveled is going to be 6 minus y sub I. Okay? So our integral then is going to be the integral, and our Riemann person needs to add up these work increments going from 0 to 6. And then we have the force increment, which is 62.4 times pi times 4/9 times y squared times 6 minus y times dy. And then you could rewrite it accordingly. After I rewrote it a little bit, what did I get? Let me see what I got. It was 62. And I think they want the answer in a perfect form, so I had to go into my modes. So my mode, I'm going to convert this to an exact mode on my calculator so I could get fractional answers. So I have 62.4 times 4/9, which is 4/16 pi all over 15. And then I have the integral of y squared times 6 minus y dy. Okay. And then you want to distribute and integrate. So this will be 4/16 pi over 15 times 6y squared minus y cubed dy from 0 to 6. So that would be 4/16 pi all over 15. Integrating 6y cubed over 3 is 2y cubed minus y to the 4th over 4. And then evaluating from 0 to 6. So I got 4/16 pi over 15 times 2 times 6 cubed. 6 cubed is 216, by the way. Minus 6 to the 4th, which is 1296 over 4. And then minus 0 for the other limit. So what do I get? 416 over 15 times 2 times 216 minus 1296 over 4. It gets 14976 over 5 pi. Okay. Let's give you a similar question for the quiz problem. We'll say this time, let's make the, so the quiz, let's see if I can get a similar problem. Give me a second. Is there any way for me to pull that off? It's just not going to allow me. Let's see if I can find one in the homework exercises. I guess problem 23. Well, that's the exact same freaking problem. Sorry. So why don't you try number 25, see if you could pull that one off. So 25 is, rather than pumping stuff out of it, you're pumping stuff into it. So it's a little maybe weird. But 25, we have a hemispherical tank. So now the radius will be constant of 6 feet position. So its base is circular. So radius is 1, 2, 3, 4, 5, 6. Doesn't really tell us. Oh, sorry, so it's not. It does have a variable radius. Sorry, it's a hemispherical tank. So problem 25. What is it? The base is, it's a hemispherical tank of radius 6 feet. So the tank looks like this, right? For the cross section, we kind of see this hemisphere. How much work is required to fill the tank with water through the hole and the base? The source is at the base. Okay, so you want to basically fill this thing with water, and here is our particular slab, which will be a disc like this. Okay. And oops, and obviously another mistake, it's the radius is 6, not the diameter. That's always a nightmare when you screw that up. So 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so let me at least try to set up a little bit of it for you. So again, what's happening here, the hemispherical tank of, this is the video quiz, by the way, hemispherical tank of radius 6 feet is positioned so the base is circular, so we got the picture going on. How much work is required to fill the tank with water? So water, again, the density for that is 62.4, so we need a sort of a weight increment. So it'll be 62.4 times the volume of the particular discs that are being put in the, sort of pushed into place. So the volume, pi r squared h. So I need a formula for the radius, because it is variable for any given position y sub I, it's going to change. So you need the formula for a circle of the upper hemisphere. In terms of y, that will be x equals the square root of 36 minus y squared. And the deal is now that we're pumping the water into it. So that disk you see there, well, let's put it one thing at a time. Let's put it into the, put this formula in for radius. So this will be 36 minus y squared. So for the work increments that the Riemann person is collecting, if you look at the picture as I have set it up here, that one rectangle has been moved from the bottom right here into this position right here. So that's the distance traveled. Okay, so it's going to be the force increment times the distance it has to travel to get it to its position. In other words, you're pumping that water into the object. That distance is just going to be given by y sub I, right? In other words, if you had some other position, like maybe you were worried about this particular slab, in order to pump it into the hemispherical tank, you have to pump it from here to there. Okay? So if it's at position 4, you have to move that disk 4 places to get it to where it is. Okay. Okay. So then ultimately your formula is going to be the integral from 0 to the top part 6 of the force increment times the distance. In other words, you're just adding up all these work increments. So it'll be 62.4 times pi. Squaring that square root gets rid of the square root. So you get 36 minus y squared times the y sub I part. Just put y, and then times dy. Then we'll leave that integral to you, but the answer is there, 20,217.6 pi foot-pounds. Okay, so that's the video quiz. And usually we're for our problems in the homework, we're pushing the contents out of the tank. But just for that one, it seems we're there's a little bit oddly oriented in that we're pushing the contents into the tank. So that's why the formula for the distance traveled is changed. Okay, let's try number 9. We'll just kind of check off the rest of the problems here. So number 9, this time we have a cylindrical gasoline tank on the back of a tractor or something. And then on top of that, there's this pipe, maybe that it's being, all the gasoline has to be pumped out of this pipe to get to where it needs to go, the tractor or whatever. So you can imagine this is on some sort of cart. And it's full of gasoline. They have the weight density for gasoline. It's 6,600 newtons per cubic meter. Anyways, we have a cylindrical gasoline tank, 3 meters in diameter and 4 meters long, is carried on the back of a truck and is used to fuel tractors. The axis of the tank is situated on the horizontal. The opening of the tractor tank is 5 meters above the top of the tank. And then find the work done in pumping all the contents out of this thing and into the tractor. Okay, so the tractor ultimately is going to be kind of oriented right here. I'm trying to draw a tractor. Right, here's its seat and all that jazz. And we're pumping the gasoline in this thing out of it and into the tractor. We want to pump all of that stuff into the tractor. If you ever get a chance to go to the fair and see the tractors, it's always awesome. But the tractors, every once in a while, because they have the way they are, they're steam tractors, they sometimes explode. So you may want to hedge your bets there if you don't want to get killed. Don't go. But that's kind of a rarity. But if you get a chance to go to the fair this summer, you can go see those things. Anyways, really interesting stuff. But okay, back to the problem. Let's reorient things on the in the XY plane. So we're looking at the gasoline tank head on. So we're looking at this blue portion here, and the diameter is 3 meters. So we're looking at 1.5. Okay, so let me redraw that. So this position is 1.5. So it'd be 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and then the top of the tank is 5 meters above. Oh crud! So we kind of have to move this. Let me lasso it and move it. So I ran out of room there. Okay. So on top of this, I need to travel 5 additional meters. So 1, 2. So 1, 2, 3, 4. To this position is kind of the top of the pipe. So that's right here at this location, that where you're pumping the fluid into the tractor. And then so the junk that we're pumping out will have cross sections like this. So first I need to sort of get the weight of all those little cross sections, and in the tractor picture, the cross section, that's what we're looking at right now, but we need the volume for this entire thingamajig, this entire wedge that our Riemann person will collect as they run up the flagpole. Okay, so the force increment, they're giving us the density is 6,600 newtons, and then times the volume of each one of those rectangular solids. So 6,600 times that volume. So the object is a rectangular solid, so we need the length, width, and height of it. So the position is at some position y sub I, and then this dimension is change in y, and then we need this distance here, which is going to be 2 times the function that gives you that circular formula. So the circle formula is x squared plus y squared equals radius squared. So the radius is 1.5, which is 3/2. We'll square that. And so our formula in terms of y will end up being the square root of 9/4 minus y squared. So our formula then is going to be 2 times that, right? So just x equals square root of 9/4 minus y squared will give you half the distance, but we need the full distance all the way across from the left there to the right. So, all right, so what do we have? That will be 2 times the square root of 9/4 minus y squared. Then we also need the length, because what this object represents is actually this wedge, right? So this distance right here is given as 4 meters long. So it's a cylindrical tank, 3 meters in diameter, 4 meters long. So this distance here is 4 meters. Okay. So the volume, is length times width times depth or whatever. So we're looking for these dimensions, and as I noted, this dimension is 4, so I need to include that. This dimension is the 2 square root of 9/4 minus y squared, and then the height is the change in y, and so then times change in y. And then for the work increment, you just take the force increment and multiply it by the distance that we have to push each one of these volumes. Okay, so that distance is the distance from the gas tank to the top of the pipe that's feeding the tractor. So that distance is a difference between this distance, okay, which we know is 1.5 plus the additional amount to get to the top. So 1.5 plus 5 is 6.5 units. And then minus the location of that particular wedge, that red rectangle. Okay, so that is just given by y sub I. So it'll be the distance traveled by each particular wedge will be 6.5 minus y. Okay, and then loading it all into our integral, I need to integrate from negative 1.5 to positive 1.5. Okay. And so we'll have 6,600 times 4 times 2. Let me just put that on my calculator. 600 times 4 times 2 is 5,800 times 6.5 minus y times the square root of 9/4 minus y squared dy. And then this is one of those integrals where you have to use geometry to evaluate it. So it'd be 52,800 times, you want to distribute this, right? So you get 2 integrals there. So you get 6.5 times the square root of 9/4 minus y squared dy. And you use geometry to figure that out, and then minus 52,800 times the integral of y times the square root of 9/4 minus y squared dy. That thing, you could do a U sub on it, but because the integrand is odd, it's just going to be 0 because you're integrating over a symmetric interval from negative 1.5 to 1.5. Okay. So in that case, all you got to do is kind of compute that first portion, factoring out the 6.5, you get 3, 4, 3, 200, and then you got the integral of this thing, which is basically just the area underneath the semicircle from negative 1.5 to 1.5. Okay, so semicircle with radius 1.5, and so we know the area of a circle with radius of 3/2 is pi times r squared. But 1/2 of that then is what that integral represents. So this will be 3, 4, 3, 200 times 1/2 times pi times 9/4. And then at the end of the day, you get 3.86100 pi. Okay, so that's kind of the spiel for these types of problems, these pumping problems with liquid. The other type of problem are the chain problems. All right, so let's look at those. And the deal is you have some sort of tractor type, I don't know. Here, you know what this is, right? You can tell by the picture. And there's a chain hanging from it. Right? And you want to know the amount of work you have to do in order to wind up the chain. So this time, the chain sort of, they give you the density of the chain is kind of the weight per foot. Okay, so here our weight density is 4 pounds per foot. Okay, so here is just some particular wedge of chain. So the force increment for that piece of chain is going to be the weight of the chain times the amount of chain. So the weight of chain again was 4 pounds per foot, I believe. And then the length of change is going to be this delta y. And what you're doing is having the Riemann person basically run up the flagpole here and sum up all of those force increments, okay, for your work increment. And so that will just be the force increment times the distance traveled. And so the distance traveled in this case is the length each individual segment of chain has to travel in order to get wound up into the winch, right? So that particular piece of chain that I circled needs to travel this distance here, and then after it gets wound up, you don't consider it as part of the picture anymore. So it's only going to be traveling for a little bit, and then it will be done. So how far is it going to be traveling? Well, it's going to be the total distance, which is the length of the chain from the winch to the ground, which is 30 feet. So it's 30 feet above the ground, so that's 30 feet. And then minus off its position. So this distance here, you would think of it as y. So the length that little hunk of chain has to travel is going to be 30 minus y. Okay? And so you go then to your integral. We want to sum up the work required for each individual piece of chain from 0 to 30, and that will just be 4 times 30 minus y dy. Okay? And then I presume you'll be able to do that integral on your own. But overall, that's the main idea. Like I said, I'm not going to be putting these questions on the test because I'm concerned that some of you won't have taken physics. Okay, but they are in the homework, and so okay. So I hope that helps, and I'll see you next time.